let's take a little walk down memory lane back to the good old days of ODEs. And we're going to consider second order equation written in standard form. So here's a standard second order linear ODE, non-homogeneous. All right, so this guy is Ly equals F, where L is second order differential operator plus P times first derivative plus Q, right? Okay, so to solve this guy, the first thing you do is find the complementary solution. Some books call this the associated homogeneous solution. I'll call it complementary with y sub c to denote it. And so this looks like c1 y1 plus c2 y2 for some choice of coefficients c1 and c2. And so this is the solution of the complementary equation, or associated homogeneous equation. Okay, so now if we go further and we find any particular solution, so a particular solution is a yp, and so in other words it needs to satisfy Lyp equals F, the original non-homogeneous one. So once we've found one particular solution, then every solution of Ly equals F looks like yc plus yp for some choice of c1 and c2. So some choice of coefficients. And it's super easy to check that. This is just a property of linearity. So if we do L applied to the sum of these things, no matter what the c1 and c2 are, this is going to be L applied to yc and L applied to yp by linearity. And then we know L of yc is 0 and L of yp is F. So we get F. And so this is how you find the general form for all solutions of the non-homogeneous equation, right? And then, so how do you find the particular solution? There's a couple different ways. You can use undetermined coefficients, which is basically an ad hoc guess and checks method for simple forcing functions. But it may or may not work if your forcing function is too complicated. So variation of parameters is a bit more robust. It always works. And it's a version of Duhamel's principle. And it constructs the particular solution from the homogeneous, or from the complementary. So what you do is you say, well, the original thing that we got for a complementary solution looked like c1 y1 plus c2 y2. And then the idea is, let's replace these constants u1 and u2, sorry, c1 and c2, with functions. So now u1 and u2 are allowed to vary with x. So this is the variation. We've just allowed the parameters ci to vary by replacing them with xi's. Okay, and so then so some calculus and actually a little bit of linear algebra shows that you can solve explicitly for yp, and it looks like y1 times the integral from a to x of minus y2 times f divided by the Wronskian plus y2 integral from a to x y1 f over the Wronskian, where the Wronskian determinant is the one found by filling in y1 and y2 and then taking their derivatives and then evaluating that determinant. So the key thing to take away from this is that the general solution is c1y1 plus c2y2 plus something involving integrals of the parts of your complementary solution.